What is calculus? You've all signed up for calculus, and you probably have to take it because your major requires it, or you're a math major, hopefully. But what really is calculus, and why do we need it? Well, calculus studies change. Okay? It extends what we've learned in pre-calc and algebra. It allows us to explore things like rates of change, slopes of curves, areas, volumes of irregular shapes, and a whole lot more. But a lot of the stuff calculus is used for requires information from other subjects that are beyond the scope of a first semester calculus course. It is an essential tool for concepts in engineering, finance, science, and many other fields that can be used to help model real-world applications. Calculus was created as a tool for other areas, especially physics, and you can learn a little bit if you do some research about the history of calculus and the debate over who really discovered, or not discovered, but created calculus. Calculus has two major tools that we'll get into, and they're both based on the limit process or the limit concept. The limit process extends what we know from pre-calculus. We'll spend the first chapter talking about limits, and then we'll use limits to help define the two major tools of calculus, the derivative and the integral. Okay. So we're going to start first with what is a limit, what does it mean, and how do limits take what we learned in pre-calc and extend them to more dynamic or interesting concepts in calculus. So here are some examples of things we can do without calculus and what we can do with differential calculus. Now, differential calculus is usually the first semester calculus, which focuses mostly on the tool called the derivative, and we'll learn later how differentials and derivatives are connected. But without calculus, you can see over here in the top left that we can figure out the value of any function at a particular point. But what if the function doesn't actually exist at that point? We can still figure out with calculus what the value would be, right, if we could actually exist at that point. Right? What are the values of f of x as x gets closer and closer to c? Okay. Without calculus, we learn slopes of lines, right? Change in y over change in x. Sometimes we call this the rise over the run. Well, we can extend that to the slope of a curve, right? So we can talk about slopes for more than just lines with calculus. In calculus, without calculus, we talk about the secant line to a curve. And you might have learned this more with a circle. Secant is a chord that connects any 2 points on a circle, but we can also extend that to points on a curve. We can also use the limit process to figure out the tangent line to a curve, which is essentially the slope of the curve. Right? The slope of the tangent line is based on the slope of the curve. One thing you might have done in pre-calc or without calculus is talk about average rate of change. We know that if we traveled 100 miles in 2 hours, we average 50 miles an hour. But with calculus, if we know the path we took, we could figure out the instantaneous rate of change at any moment in time. These are all things that we're going to learn over the course of this first semester, and there's lots more that we can do, but just want to give you a little taste. So before, you've studied functions like this. F of x equals x squared minus 9 over x minus 3. And when we look at the denominator here, we think about rational functions, right? We have a polynomial over a polynomial. And the denominator makes us think that we're going to have a vertical asymptote maybe at x equals 3. Okay? But we can hopefully see that this numerator is actually factorable. And if we were to simplify, we won't actually still have x minus 3 in there. This won't be a vertical asymptote. Right? Now we can figure out f of 0, right? 0 minus 9 over 0 minus 3, that's just 3. We could figure out f of 1, right? 1 minus 9, which is negative 8, 1 minus 3, which is negative 2, that's 4. But what happens when we try to put 3 in? Right? We get 0 on the top and we get 0 on the bottom. right? And this becomes a problem, right? We've always learned that 0 over anything is 0 and anything over 0 is undefined. So what happens if we try to do both of these at the same time? When you learn rational functions and graphing them in pre-calculus, you might have seen an example like this as an exception to the rule. Even though the denominator of f of x is 0, we'll learn later that x equals 3 is not a vertical asymptote, and we'll help understand why. But right now, what we want to do with this example is think about how would we figure out what f of 3 is. This function exists everywhere except for x equals 3. And it turns out that we can figure out where we would be if x was allowed to be 3. Right? What a value is very, very close to 3 would produce a consistent value that we'll refer to as the limit. So this is sort of a good example and the notation we're going to use for the limit. Up in the left here, we have the limit as x approaches c of f of x equals L. So the way we read this always is the LIM is an abbreviation for limit. We have a variable that is approaching a fixed value. And then we have the function f of x, which is a function that's defined. And what we're saying is that as x gets closer and closer to c, f of x gets closer and closer to L. So for this particular example down here, we want x to be approaching 3. Right? And the question really is what's happening as x is approaching 3? Well, if x is approaching 3, right, from the left, or x is approaching 3 from the right, we're moving along this curve. Right? X approaches 3 from the left. The y values in both cases are getting closer and closer to 2. So let's take a look at that again. As x is approaching 3, right, on the curve, right, we're moving closer and closer towards where that open circle is. So the limit as x approaches 3 for f of x would be 2. Okay. As x gets closer and closer to 3, f of x gets closer and closer to 2. Now, f of 3, right, is actually defined to be 1. And this is sort of where limits become important and a little bit hard to wrap your head around at first, but hopefully you'll get used to it. F of 3 is where the function actually is at 3. And in this case, the y-coordinate of 3, or the output value for f of x at 3 is 1. But the limit is not necessarily the same as where the function actually is. The limit is where the function is heading towards. In this case, the closer x gets to 3 from the left and from the right, the closer f of x gets to 2. Even though once we actually get to 3, we don't end up at 2. So the limit is really about where you're headed towards, and the function value is really where you're at. Now, through most of your algebra and pre-calculus career, they're one and the same. We don't often see functions like this with holes and disconnected graphs, but we're going to study those in a little bit more detail to make sure we really understand limits, and we'll define continuity in a more formal way as we start to work with a more formal mathematical language. But this is how we deal with limits. This is what a limit is. We'll find out that not all limits exist. We'll spend lots of time looking at all sorts of different examples. But we just want to try to wrap our head around this notation and see how we can figure out limits. We'll look at one more example when we don't have a picture that'll help lead us eventually to what we're looking at. So this is a sort of complicated function up here, x minus 5 over x plus 4 minus 3. And, we could sort of say, well, let me just hope that this function is continuous and where it looks like where we're headed is actually where we end up. So we'll just try putting 5 in. And if you put 5 in the top, you get 0. If you put 5 in the bottom, 5 plus 4 is 9. Square root of 9 is 3, and 3 minus 3 is 0. Right? So we're getting one of these 0 over 0 cases that we can't resolve. So we can try looking at a picture, but we don't know how to graph this, and I don't have this graph available. So another option is, what does it mean for x to be getting closer and closer to 5? Well, we could start at 4.9, and then look at x becoming 4.99, and we can start getting closer and closer to 5 from the left. We could start at x being at 5.1, 5.01, 5.001, and look at what happens when x gets closer and closer to 5 from the right. And we can look at the y values that this function is producing. If you get your calculator out and you're careful with your order of operations, you'll find out that f of 4.9 is 5.98. Similarly, if you put 4.99 in, you'll get 5.998. Okay, I've done these calculations already so that you won't have to. When you put in 4.999, you get 5.998. Okay, let's keep this centered. When you put 5.1 in, you're going to get 6.02. When you put 5.01 in, you'll get 6.002. And when you put 5.001, you'll get 6.0002. Now, as x is getting closer to 5 from the left, it looks like the y values are getting closer and closer to 6. As x is getting closer and closer to 5 from the right, it looks like the y values are also getting closer and closer to 6. Now, it's certainly possible that this function would be heading towards 6.000000000013 or 5.999999997, but it's pretty unlikely, and we'll be able to have a more sophisticated method as we learn more about limits to figure this out. But our best guess from this numerical approach is to estimate that the limit as x approaches 5 of this function x minus 5 all over the quantity square root of x plus 4 minus 3 is in fact 6. So right now we're focusing on how to use graphs to find limits and how to use numerical methods to find limits. There's certainly a lot of button pushing on a calculator to do the numerical approach, but I think it's important to always remember that behind every limit we do, even when we learn more sophisticated methods, is to think about what a limit really means. As x is getting closer and closer to the value in question, are the y values getting closer and closer to some other value? Whether we do it by looking at numerical values in a table or looking at a graph, right? As x gets closer and closer to 3, are the y values getting closer and closer to some value? That's what this limit notation means, and that's what the limit concept is, and that's what we'll be working on at the beginning of this course.